Hello again, folks, in 113. Today we're going to be starting a new chapter, which will be chapter 11 on probability, specifically 11.1. Here's the calendar to confirm that we're on schedule. Let's see. Okay. Yep. Okay. Today is Tuesday, April 11th. Pardon me, I'm on a time warp here. Tuesday, April 13th, so 11:1 per the schedule. Very good. All right, the packet that I have for you is as always a mix of my materials and books materials. I'm going to lean on my own more so this time, but I did include both. Here's a diagram again, just because there'll be some terminology up front. This is sort of a hybrid. I stole this from the textbook, of course, right? But I augmented it. Right? I didn't think it was clear the way that it was written, so I just I drew on top of it. I hope that that's helpful. All right, this is again, this is my own creation, but I basically took the information from the book, as I would, and I sort of added to it in this case. Just some facts that I think make it a little bit more easy to understand. There's a lot of information here. I left this in. Normally I wouldn't bother, but this I thought was very interesting. It was about the history of the subject, with pictures too. So there will be the textbooks, formulas and tables and definitions that you could utilize in lieu of my own if you prefer. And then there's finally the examples. I shouldn't say finally. I'm not going to use all of them. I think I'm going to do 1, 2, 3, and 5. 4 I found kind of dry. And then I threw in one that I had from ages ago. That was from a different textbook. That to me really gets the point across, and it's a lot more fun. It's about food. All right, so we'll go into that. This book discusses genetics a little bit, so I mean, it would be appropriate, of course, but they didn't give you any examples pertaining to that, really. Maybe 4, but not what you would think. Anyhow, I'll discuss that just as an afterthought, all right? Anyhow, just to show you where we're headed, all right? Of course, as I said, we're starting chapter 11, so if you want to just make a partition, perhaps, in your notes. This is where it would start. We'll begin here. There's my glasses. Here we are. Okay. Basically, this is the rundown. What we're doing today is just an introduction to probability. All right, so some definitions, some formulae. All right. What you'll see, and I think this is really the reason why I mention it, is that when we get to 11.2, so on Thursday, right, we'll begin the discussion of odds, right? And a lot of times people confuse or conflate these two, right? But they're not exactly the same thing. They're related, of course, but how you would read odds is derived from probability. They're not exactly the same, all right? Moving along, when we get to 11.3, there'll be the subject of expected value, which is a formula. And let's see, 11.4 is some diagrams, all right, some specifically what's helpful in the subject of probability tree diagrams. You probably have some inkling of this if you've had any math in high school. Then 11.5 is about compound probability. And to contrast with that, we have something called eventually conditional probability. Okay, so we're not going to do all of this in one day, of course. We are, per the schedule, right here, right at the very beginning, all right, an introduction. So it's important to make sure that we nail down some terminology, all right, first and foremost. All right. So let me do that. The reason that I labeled this MAT-113 stats is because this is the extent to which you would see statistics in MAT-113. If you stick around for MAT-114 next semester, all right, there's chapter 12 was dedicated to statistics precisely. All right, probability is a subject that usually comes up in tandem with statistics, so I felt it was appropriate to label it as such. All right, I would, if you wanted to, write those things in the same notebook, because in a full-blown statistics course, that is a course dedicated to statistics, not just incidentally, you would very likely broach the subject of probability once again. Now, as for terminology, let me turn my little projector here, and we'll get rolling. We may have to adjust the blinds. Okay, there's the faithful homepage here. All right. Yeah, that definitely needs a little adjusting here. This is as bright as it's going to get, huh? Okay. I think it's visible. I should enlarge it just a wee bit. Just to capture some terms here. Let us start with an experiment. All right. An experiment in the context of probability. I'm going to put that under here. Context is uber important, for lack of a better phrase, because it specifies, the actual meaning. Because you could do that word experiment, like many words that are ambiguous, could mean different things. All right, an experiment in the context of probability is basically a game. That may sound silly, but it's true. All right, all right. If you want to be very formal, all right, or more general. The textbook has it defined this way: a controlled operation, not untrue. All right, that yields a set of results. There's two key phrases here. All right. If you really want to get a feel for it, it is literally a game, all right, in the context of probability. It's funny to think of an experiment as being something that's playtime, but it really can be if you think about it. I'm going to close this door. More things are game than are given credit as such. Anyhow, it is a controlled operation that yields a set. So I'm going to remind you, just by accenting this with fancy braces, all right? Remember a set, all right? Earlier on in the semester, we had discussed the concept of sets and set notation. So we're going to borrow that notation, all right, just to emphasize. Because you remember from set notation that what is a set but a container, really, with a lot of different things in it. And it's usually a list, right? In its most basic incarnation, it is a list of different items, or elements, we would say. Now, it's a set of results. Circle that. All right, because there's a phrase for that. Outcomes. Outcomes are the possible results of the experiment. I'm going to get out of the way, I swear. All right. The possible results of an experiment. So what does that make it most akin to? All right. using different terminology. They're elements of a set. The slew of them, right? The elements are the results, otherwise known as the outcomes. This is another instance of math and English at large, all right, where it can be a little confusing because we have a lot of words to describe the same thing, all right? Outcome is more or less the favored term, though, in this context. All right. Then there is an event. All right? An event is usually in abbreviation, so I use a symbol finally, E. It's usually in a parentheses as well. All right. I'll just leave it stand alone for a moment. E is my fancy E. And that would technically be any subset of the incomes. Outcomes. I wish it was incomes. Got my mind on my money. It's tax season, right? Any subset of the outcomes, that is the same thing as, again, saying results. Right. Remember, though, when it comes to subsets, it could be the whole thing. Could be whole. It could be part. Or it could be nothing. All right. When we talk about a subset, anyhow, whole or part, all right, typically in this case, all right, and then there is finally the definition for probability itself, all right, so I'll put that in here. Probability. I have a tendency, I hope you will forgive me, to abbreviate PROB just because it seems to expedite my writing. The symbols that you will see is a capital P and then, as if it was in function notation, empty parentheses. So then the element, the event, whatever is being described, would be the inside of this, right? And you would read it as the probability of the event, such and such, you know. Or sometimes you just see it as P of E. That's very much like function notation. All right. What is probability in a nutshell? It's a number. It's a number that is meant to give us a feeling. All right. Used to describe the likelihood of an event. How likely it would happen. The likelihood of an event occurring. Maybe that would make it a little bit more reinforced. So they have that occurring. Right. Okay. So here's where we're at in terms of terminology. All right. An experiment is a game. An outcome is one of the possible results of that. An event could be a cluster, essentially, or it could be one individual. That is to say, in the context of set notation, any subset of possible outcomes. Normally when we talk about subsets, right, it could be the whole thing, right? Every possible outcome. It could be part of it somehow. It could be one thing, it could be several things that we're considering. Or in the context of subsets at least, it could be nothing, an empty set. All right. This is not something I believe you would see too often, all right, in the case of probability, if at all. I'd have to consider that. All right. The situation where you have nothing. in which case you would say 0 in that sense. But what I mean is that you wouldn't have, there's no such thing as an empty set, really. Right? In other words, you won't see something like this. The probability of an event is an empty set. Right? They would, instead of doing that, would just simply say 0. The probability of an event is 0. Okay. Not trying to get myself in too much trouble here. Moving on. Let me draw you a diagram now to summarize the various types of experimental games here. Turn off, please. And hopefully my eraser and my markers will cooperate. Hey, look at that, they erase. The blue is kind of lingering, but hey, whatever. There you want everything. Yes. Okay. All right. Now, let me choose a different blue here. There are. My black markers are very nice. All right. 3 basic probability experiments. I.e., in other words, games that you are likely to see. Okay. There are coin flips. And there are die rolls. And there are, please green work, card draws. Is that visible? Turn the lights if that helps. That's maybe a bit better, right? I'll leave it like that. There are coin flips, die rolls, and card draws. Well, what does that mean? I made some props. I'm trying to set a good example here. All right. As I think I mentioned to you folks before, if you go into the field of teaching, be prepared to recycle a lot of garbage. All right. And then when you see garbage, you're gonna go, I could make that into something. I should save that. It's very easy to become a hoarder, is what I'm getting at. Here is a piece of plastic that I found in a car. I don't know what it is. I think it's part of like somebody's stereo or something. Anyhow, I made a heads and a tails. All right. Why? Just because it's a little bit larger than a coin. If it was truly fair, it probably wouldn't look like an Oreo cookie either, that it has this sort of adhesive on it. But you get the idea. A coin flip is the most basic probability experiment, i.e. game, right? Where there are 2 possible outcomes. There's either heads or there's tails. Right? So what do you do with it naturally? You just flip, all right? All right, and then you read it as it lands, of course. All right. So, in the context of a set, all right, once again, there are 2 equally likely outcomes, right? So, if I were going to write it, I mean, this may be overkill, and I'll move my fake dice for a moment. The set would be, I'm going to put in fancy braces, right? Literally just 2 things, right? Heads, comma, tails. Right? 2 equally likely outcomes, heads or tails, right? Actually, this is not to get myself in trouble again, but if you're a fan of the old the original 1960s Twilight Zone, there's an episode of the Twilight Zone when a guy's buying a newspaper, so he just sort of throws a quarter, right, at the newsstand attendant, right? And instead of it landing flat one way or the other, it actually lands right on its edge. And for the rest of the episode, he has the ability, inexplicably, to hear people's thoughts. All right. Anyhow, that's probably not going to happen. If it were possible, it would be literally as slim a possibility as as could be. All right. Anyhow, we're going to pretend that that is not an option. That a coin is, in theory, perfectly mathematically flat, meaning that it doesn't have a thickness. There is no edge, right, in the mathematical perspective of it. So it's either this or it's that, right, and no third option of an edge, right? Die rolls, on the other hand, right, is a little bit more complicated, right? I made these, as I mentioned. I had some styrofoam, I don't know, like either me or my sister had ordered something, and the box came with a pretty hefty chunk of styrofoam. So, again, being the prospective hoarder that I am, all right, I cut them up yesterday, all right, only for the reason that it's a little bit easier to see something that is this size versus an actual die is usually that tiny, and I'd have to go digging up my Monopoly right now. Anyhow, I don't think my sister cares that I tore up the styrofoam. And I decorated it with dots. And just to make it distinct, I made this red. I get so happy when you make garbage into something useful. It's repurposing, right? Anyhow, if you examine just one individual die, the plural being dice, all right? How many faces of a cube, because that's the basic shape of it, all there? Right? How many faces would there be? It would be just 6 total, of course, right? Which means that in terms of unique possible outcomes, all right, it would be just 6 possible outcomes, which is not too bad, right? There are 6 equally likely because it is a regular polyhedron, right? 6 equally likely outcomes, and if you were going to describe those outcomes in a roster form, then what would they be, right? 1, 2, 3, 4, 5, 6, right? That is the whole thing, the whole kit and caboodle of possibilities. All right. The uniformity of the shape really is what makes something equally likely. I suppose if this was not quite a cube, if it was something less regular, then it would be not a fair die then, right? So it's very important that you have a regular symmetrical shape here. All right, now the last thing, as far as the 3 basic experiments games are concerned, is the card draw. So that's a little bit more complicated because we have a multitude of more possibilities, right? If we're just talking about the cards themselves, and I'm taking the jokers out of the deck here, all right, and the receipt here, I don't know why they have that, and the advertisement from the 90s, all right, you could see that you have, not to be a magician, but quite a few equally likely choices. Never mind what the cards are themselves. Maybe it would be better initially to think about it this way. All right, look at them not at the unique faces of the cards, the numbers even, all right, but just the back of the card, whatever that pattern is. Essentially, they're all the same, right, from this perspective. So what does that mean? Well, this is a polka deck. So in theory, there are, in this case, 52 equally likely outcomes. I have to say a polka deck because there's pinochle decks. I've never played pinochle, but I know that the decks are a little bit more complicated. All right, a standard deck that you buy at the supermarket, all right, is 52 playing cards. All right. What I should do is give you some inkling as to what that contains. All right, this is a standard poker deck. Not a pinochle deck. There are officially in that sort of purchase, these parts. There is basically 1 to 13, if you want to think about number 1 to number 13, of 4 suits, which means this. It means there's one is the ace card, essentially. So you can have an ace of hearts all the way through a king of hearts. That is essentially the same thing as 1 through 13. Okay. You have a next suit would be a spade. So an ace of spades all the way through a king of spades. And then a third suit, which would be diamonds. So ace of diamonds, ace 1 essentially, through king of diamonds. And then clubs. Ace of clubs through the king of clubs. That would be essentially the set. I'm just trying to spam myself, so I'm kind of cheating here. All right, but you get the idea. 1 through 13 of the heart suit, 1 through 13 of the spade suit, 1 through 13 of the diamonds, 1 through 13 of the clubs. And I alternated in this pattern because if you're familiar with playing cards, they usually like that. The hearts are red, obviously, all right, and spades and clubs are black, and diamonds happen to be red as well. So there's 2 colors overall, red and black. Like Alice in Wonderland. Right. Don't take for granted that your students, especially a little kid, has ever touched a deck of cards. Right? I made that mistake a long time ago, and it really opened my eyes. Right? That sounds silly, I suppose, but right. When I was teaching middle school years ago, right, I had assumed wrongly that every child had played with a deck of cards, but that isn't always the case, so one cannot assume, right? It could be for religious reasons, I suppose, all right, or just, I hate to say it, but, they just, a lack of interest, all right, or, extreme poverty, all right? So that may sound silly, right? But, like when you're trying to decide between eating and, playing a game, you might decide eating instead. You can't eat peas, all right? So never assume that your students are familiar with anything, all right? Even something as you take as mundane as a deck of cards even, all right? And explain the intricacies of it, let them play with it too. It's just a game, all right? Anyhow, there are the face cards, of course, too. Here you have these lookers that we have here. The jacks look so morose. The kings and so forth. There are queens that are picture cards, jacks which are lower, and kings, right? Essentially, if you have aces 1, and then there's 2, 3, 4, 5, 6, 7, 8, 9, 10, there are face cards that start with jack. So jack is basically an 11, all right? Queen is the next one, it's 12, and kings are 13s. Right? They just don't label them as such. All right, now let me put those away just to keep them from going all over. All right. So that, as you can see, in the case of a card drawer, right, this is the most sophisticated or the most complex potentially of the basic probability experiments. Visual aids are very useful as well. Again, why did I bother to make something like this when I could have just used a regular die? All right, because it's larger. Right? Years ago, I used to have quite a hefty one. I had taken a workshop, and the professor of that workshop is such a good man. He made us giant-sized die, bigger than even fuzzy dice that you would see on somebody's dashboard. All right, at least that wide, Okay. Okay. One other thing, right? A set, which is again usually written in fancy braces, right? In the context of probability, is often referred to as a sample space. So that being the phrase of choice in the context of probability, the abbreviation very often for sample space is just the capital S. Right? When you see the formulae and you see a capital S in it, it's referring to the whole kit and caboodle, the whole sample space, the whole set. All right, just beware. Okay. Now, having said that, I'm going to move on here. Now, there are, and this is where you could, if you wanted to, you could rely on the textbook, but I like my little diagrams, so I'm going to give it to you. There are basically two types of probability that we will be concerned with. There is, firstly, what is known as theoretical probability. I hope that that's legible. I'm sorry for the sloppiness. Bit of a glare, right? That's better or worse. That might be a little bit better. Okay. Theoretical probability. Small because I want to get to be a dud. And experimental probability. There's an alternate name for this experimental probability that your textbook favors instead of the word experimental. And so I will write it just a moment. That's getting to be a dud too. Okay. The favored term here is this. If you don't see the word in the instruction experimental, which is literally what it is, right? There's an actual experiment going on, an actual game, right? An actual game. Underway. Then they will use this phrase, empirical. These are synonymous terms. To be empirical is to be experimental probability. Okay. Now, in the big picture, the difference between these two things, this is abstract, right? Meaning it's something going on in your head, in your mind. It's a thought experiment, right? More or less a thought experiment. It's not a real thing, right? It's in theory, right? This is, again, a concrete situation, real life, right? Real situation. which is why I say an actual game underway. Right? Let's see. Sorry, I'm itchy suddenly. Right. An actual experiment. As opposed to a thought experiment. That's an E, I swear. Okay. Now, they're really the same level of sophistication in terms of the math involved, but the labels are different to describe or collude with the situations that are ongoing here. So let's start with this because this is the foundational concept, right? The formula that you would see, the way that it's written in shorthand notation would be this, right? P, parentheses, and then whatever the event is, right? I'm gonna just put this in red to distinguish the parts here, right? Not to conflate it with that, it's just that I have very few colors, all right? All right, the probability of the event. The likelihood of the event, whatever it is, right, is equal to, right, this shorthand notation to continue. The cardinal number of the event. That's using the context of set notation again. Over the number in the sample space. All right, there's a lot to that, so I will. I promise you, I'll put some labels to make it a little bit more obvious. Okay. The context that we're familiar with, again, in theory, is the context of set notation, which is the only reason why I say n parentheses e is the cardinal number, right? It's good to fall back on that because it's it's pretty basic, right? Cardinal number is what? The number of numbers, all right? So in the phrasing of probability, they would say it this way, right? The probability equals the number of events or outcomes, rather, favorable to the event, whatever is being described. Right? That is summarized by this sequence of symbols, right? N, parentheses, and then whatever the unique event is. This is a generalization, right? All right? Divided by, right? This is the number of possible outcomes. The total number of possible outcomes. I'm encroaching on my own little board here, but I have no choice. Oh, brother, why can't I write? The total number of possible, that's where those are two S's, outcomes in the sample space. Hence the S. Or in the set, whatever you prefer, really. Right. It's still borrowing, again, I'm sorry to belabor the point, but if it makes it more understandable using the older terminology, then so be it, right? That's the beauty of math, right? We're building upon something that we already know, so the symbols are the same, right? It really is the same thing, it's just changing the context slightly. This is a cardinal number, right? So a cardinal number is the number of numbers, right? Specifically, the number of numbers that are favorable to the event, right? This is the cardinal number of the sample space. So it's the total number of possible outcomes in the whole set. I erased what I wrote from before, of course. All right, having a flashback. All right, digest that a moment, and I will groom my ugly self here. All right, I'll take a sip of water. All right. All right. When to use this? Theoretical probability, just because I need the space, I'm going to erase this up here. When to use this versus when to use this. This gets used appropriately if all events are equally likely. Pardon me, if all equally likely outcomes. We could use this as a model, basically, this particular incarnation of a probability formula, all right? If all the outcomes discussed or under consideration are equally likely, all right? Now, again, that would be appropriate in each of these situations, all right? Whether you have a coin of some sort, all right, a card draw of some sort, or a die roll of some sort, because there's uniformity there, all right? The cards, the back of them are all the same. So if that makes you blind to when you're drawing them, therefore they're all equally likely outcomes. All right. A die roll is if there's uniformity in the actual three-dimensional object. All right. It's just going to land wherever it lands. All right. There's, as far as I can tell, really no skill involved in doing that, in rolling a die. Some might argue. And in the case of a coin, we're assuming the situation is mathematically flat so that there is, in theory, no thickness, no edge, really. All right? All right? Equally likely, all right? Heads or tails. All right? All right. Now, in the case of experimental probability, when is this used? All right. You could do it in real life anyhow, in any event, but it's used a lot when probability cannot be theoretically calculated. Now, what is an instance in which the probability cannot be theoretically calculated? You could do experiments regardless of that, but if you have no other choice, you would have to use experimental probability in this scenario. Right? The example that your book uses is pretty good. All right? Life insurance companies, for example, right? What do? Right? They try to link profession with life expectancy. All right? All right? They can't kill anyone. Thank God for that, right? Imagine the life insurance company just kills people to do an experiment, right? But they will basically analyze given data, all right, actual real life, statistics, all right, and they will try to correlate life expectancy with a particular job, a profession, right? They want to link a profession with life expectancy. I hate to say this, but like, if you're a person who has done grueling, manual labor your whole life, right? That puts a lot of stress on your body naturally. All right, so your life expectancy might be lower as a result of that. If you work in coal mines, for example, right? The coal miners, right? They get black lung from being in breathing in toxic dust basically for their whole careers. All right, so their life expectancy would be potentially shorter, right? Or they might be more likely to get certain types of diseases. Right? It's awful. All right. But anyhow, the life insurance company tries to use that actual real life statistical data, right, to link a profession with a life expectancy. All right. Now, the formula that you're going to see for experimental probability is the same basic idea. It's a number on top of another number, but the labels are different, right? Because of what is actually going on. This is real versus something that is abstractly in one's mind. So what you will see in this case is the probability function, if you will. It's not really a function per se, but just to give it some emphasis to distinguish one part from another. I'm just using two different colors here because I'm limited in my palette. Right? The probability of a certain event, an experimental situation, is equal to a slightly less ugly formula, perhaps. F over N. Right? And this might be even a little bit more intuitive. F as in frequency. Right, which is what? The number of times something actually occurs. Actually occurs. Event frequency, I should say. That is the number of times it actually occurs. The N value that you see here, all right, is not the number of things in the sample space, because again, this is an experimental situation. What the N is in this case is the number of trials I'm going to erase this just because I need the space here. The number of trials of the experiment. Do you do an experiment one time or do you do it multiple times? Usually it's multiple times. That gives it more gravitas, right? If it's, what's the word, repeatable. Right? If you have an experiment that, just dumb luck, worked out in your favor, right? That's really not enough in a scientific sense, not in an empirical way. All right, but these are not really the same thing, the denominators. They're a number that is filling in that void, but this is the number of things that are possible in the sample space. This is how many times you run the experiment, the number of trials. All right. I think that is sufficient in terms of contrasting the two, and I'm sorry I'm standing away. Let me move. Let me do some examples with you, all right? And then we're going to come back to this contrast in a few moments, but I want to finally get the satisfaction of doing an actual problem. All right, so let me erase this now. All right, remember these formulae. We're going to start with theoretical problems, so it's really this incarnation of the probability that we'll be considering first. All right. I don't like the way that, this is the only downside. The book is a nice book, but I don't like the order in which it presented the material personally. Water. Okay. I'm going to, I'll show you this first, just not to have to turn the projector and then off again. It's not really imperative. Let's skip over to what would be technically example 3. We'll do this multi-part example here. All right, so number 3 to start with. All right, and I'll sort of abbreviate the instructions right here. See if this is legible. Example 3, technically, is what is referred to. In a fair, meaning no cheating, no rigged dice, in a fair die roll, right, determine the following. Right, and since this is 1, 2, 3, 4, 5 parts, right, I'm going to chop up my little board here into a couple of columns, just not to have to erase. Right. A, B, C to get rolling, and then eventually D, and then E. All right. The first one is just written as this much: P parentheses 2. Right. All right. P even. I'm abbreviating a little bit myself. I'll leave that one because I want to show you how to sort of do your own abbreviations if necessary. And there's a skill to that too, I would argue. All right, and then this one down here. There's another one worthy of all time. All right, the way that it is actually written, all right, it asks you in a fair die roll to determine the probability of rolling 2. All right. So how would you take that in verbal English, right, and translate it into something that is more concise and universally understood? All right. P for probability, of is what the parentheses is implying here, and then since we're talking about a die roll, rolling a 2 is just enough to say put the 2 in here. All right. Now, if we borrow the formula, all right, the formula is again the number of events that are favorable to 2. So you might write it as n parentheses 2 over the number of possible outcomes in the sample space. So every time that you do this, you would put the actual same event here and here. And then maybe I'll just put it on the side because it's a little bit more intuitive that way. All right. And then in the denominator, just put the cardinal number of S, basically, because it's the sample space. All right. What you might do as a favor to yourself before you even begin is actually list in roster style the sample space. All right. So I'm going to do that over here. All right. The sample space is for a die roll. All right. What again are the from the basic probability experiment / games? What are the possible outcomes? All right. Well, again, I took the time to make one. Right. You would have to examine the dots on a die. I tried to be consistent with the style that you would likely find in a store. All right. There's 1, 2, 3, 4, 5, and 6 dots, right? So there's 6 sides total. They don't roll that well. That means that in the sample space, the possible outcomes would be 1, 2, 3, 4, 5, and 6, right? All right, nothing modulo here. We're not starting with 0. It's always the reality of the situation. Okay. So, although it could be a little confusing, right? Read this again in the old set notation style of reading it. What is the cardinal number, all right, of elements that are 2, right? How many things, all right, what's the number of numbers? How many things are labeled 2? in the sample space. There's just this one thing that is labeled 2. So therefore the top number is 1. Right? What is the number of elements in the sample space? 1, 2, 3, 4, 5, 6. So that means your denominator is 6, and therefore your probability is 1 out of 6, right? If you want to, you can translate this into a percentage, right? We'll get into that in a little bit, but for right now, it's usually just a fraction, right? 1 out of 6. Probability. 1 out of every 6 rolls, which is not too good, really, would be a 2, right? Then when you get to this problem, it asks you, all right, what is the probability of rolling an even? Right? How do you, again, that's how it would basically be written in grammatical verbal English. All right, how would you take that and translate it into math speak, for lack of a better phrase? All right, a more concise, universally understood concept. I abbreviated it this way because I felt it was the most intuitive. The probability, the P of even, right? Given this situation, a die roll, 1 die, right? If I just wrote it here, right, underneath it, for the sake of comparison, the probability of rolling an even is equal to the number of events favorable to rolling an even, right, over the number of elements or outcomes in the sample space. Right, so the situation, we're just going to borrow that, and then the bottom is pretty much always the n of s, right, the set, right. Okay, so if you go back to the sample space, right, the set basically, that might be a little bit easier to read it that way. This is a set. I'm thinking too much into the future, perhaps. All right. How many things are actually even? Well, 2 is even, 4 is even, and 6 is even out of these elements. So how many is that total? What's the cardinal number of that situation? Right. It would technically be 3, right? What is still the total number of outcomes in general? 6. Right? If you took this fraction, 3 out of 6, which is totally correct, right, and then simply reduce the fraction, what would you get? You would get 1/2, really, right? The probability of 1/2, right? Which again, you could convert this to a percent, right? In the case of 1/6 from before, that's about 17% chance, right? Versus this is evidently, exactly a 50% chance. Much better, right? You're very likely to roll it. Well, you're just as likely to roll an even as you are to roll an odd, right? Given a 6-sided die. Okay. Then there's this situation. I decided when I was prepping this, as you saw, not to fill this in because I want to negotiate here. The question is originally, what is the probability of rolling a number less than 3? That's very verbose, right? This is essentially as it is written, a number less than 3, pardon me, greater than, what am I saying? All right, greater than, inventing a problem here. All right, what is the probability of rolling a number greater than 3? Take that and again, translate it into math speak. What is a logical letter to represent a number? All right. I would argue that n is a logical number, right? Because it's the initial of it, right? The first initial. What is the symbol, the mathematical symbol for greater than? Well, it would be oriented like this in relation to n. A number bigger, essentially the open end of this, right? And then the Hindu-Arabic numeral for 3, right? So this is a much more concisely written instruction. All right. If you understand already that we're talking about a die roll, it shouldn't really be any more complicated than that. What is the probability of a number greater than 3? All right. Well, here, I'm going to write it again sideways. It would be, to borrow the theoretical probability, the number of events favorable, the number of outcomes, I should say, favorable to a roll greater than 3. This is unfortunate because there's the n as in cardinal number, and then there's the number that I'm using here in this context, right? It happens sometimes, right? I could stylize it, give it a little flair. All right. The number of outcomes favorable to a number greater than 3, right? Over the number of elements in the sample space or in the set. Right, the cardinal number, that is. All right. So let's consider it. All right. I have to erase a little bit what mess that I've made here, so I'll change these circles. All right, here's the set of elements. All right, how many things are greater than 3? I mean, you might conceive of what is naturally greater than 3 in terms of, natural numbers. All right, 4, 5, and 6, right, out of these choices. So these 3 things. All right. So once again, the number of outcomes favorable to rolling a number greater than 3 is in fact 3 itself. Right, just coincidentally. How many things are in the set? It's still 6. So what does that mean? This is still a half, which is still a 50% chance. Right? If you're a little worried about, like as before, hey, how'd you get 17%, buddy? I'm going to talk you through that a little bit. It's dividing the top by the bottom and then multiplying by 100, which is the effect of just moving a decimal place 2 spaces to the right. All right, that's old hat, but, never assume that anyone remembers it. This is still a 50%, 1 out of 2, 3 out of 6, whatever you like, situation. All right, now we'll do the last 2, and in that event, just for the sake of not having to suffocate, let me erase a little bit up here. And scoot up a wee bit. All right. This question was the probability, this is D, the probability of rolling 7, right? That is pretty simple at this point to translate into math speak, right? Probability of rolling 7, it is sufficient to put P parentheses and then a 7. All right. All right. Remember, if we're using theoretical probability, and again, this is totally abstract, I'm not rolling anything, you would write it like this. The number of outcomes favorable to rolling a 7, right, over the number of total possible outcomes in the set, sample space, whatever you want to call it. All right. Now analyze, this is something of a trick question, right? And I'm sure you won't be deceived, but humor me. Is there any situation on a 6-sided die that and this, we're just talking about 1, mind you, 1 die, not 2 dice. All right. Is there any side that is actually labeled 7? Right? No. All right. So what would you have to put here in place of this abbreviation? Just 0. All right. How many events are total possible? It's still 6. All right. So you could leave it in the style of a fraction, 0 out of 6. But if you did the arithmetic, what's 0 divided by almost anything? This would just be equal to 0, which would be exactly 0%, right? This is not about equals, that is exactly equal to, right? Just as this would be exactly equal to. All right. I rounded the 1/6 from before. All right. Last one of this sort. All right. E. What you're asked in this situation is something similar to this one. So let's dissect it. All right. What is the probability of rolling a number, in this case less than 7? To translate that into the abbreviations that we are growing to love here, all right, again, a number is, understandably, you can put an X if you like, but maybe I should just not to conflate it with the cardinal number, but N as a number, right, less than 7 is pretty universally understood, right? The probability of a number less than 7 in a fair die roll, that would be equal to, again, the number of events, outcomes favorable to this situation over the number of total possible outcomes in this set. Right. It's renovating if you hear any saw noises going on. All right. What is less than 7 in this universe here? All right. Everything, right? That is less than 7, that is less than 7, so is this, and this. The whole kit and caboodle, right? So this figure would be 6, and again, how many possible outcomes are there in general? Still 6. So what does that mean? It means that you could write it as 6 out of 6, or 1 over 1, or you could just simply write it as 1, right? In which case, in terms of a percentage, because that is sometimes more warm, fuzzy, and familiar, that would be 100% possibility, right? We went from having 0% never gonna happen possibility to this situation where we have 100% possibility, absolutely certain, right? Okay. Now, having said that, not having said that, I don't want to tell you contrast here. Let me consider the examples that we have that are empirical, so-called. Right? I'm going to do example 1 and 2, and walk you through some diagrams. These were all theoretical possibilities. These are abstract. They didn't actually occur, except in the twisted alleyways of my mind. And yours too. Okay. Here, that was example 3. Let's go through example 1 and example 2 here. 2, I may turn on the projector, but for 1, I think I can get away with this. Example 1 from the packet is essentially this. In 100 fair, meaning no cheating, no rigged coins, coin flips, determine the empirical, aka experimental, probability of landing 44 heads. All right, that is my paraphrasing of example 1. Right? Now, if the situation is, this is in theory, and I hate to say that because it's, a contradiction really. If we were to really do this, and this was the outcome, all right, 44 heads, all right, and that would be an empirical experimental probability, which means what? It means that it's this incarnation of the formula for probability that we would technically use, right? It's still basically a ratio, a fraction, all right? Something over something else. But what we would have to write here would be the following, right? This would be the frequency, again. Let's see how I labeled it. All right. That is the number of times the event actually occurred and this would be the total number of trials. Of the experimental game or what have you. Okay? We're pretending for a moment that this really happened. All right? So, they describe it as being 44 heads. Right? That means, in theory, that if you were to flip a coin 100 times, not necessarily in a row, right? It isn't saying anything in a row, but overall, right, that it landed on heads exactly 44 times, right? Face up, heads, right? So the frequency would be logically 44 right here on top, right? How many total number of trials of the experiment occurred according to the description? 100. So you would put a 100 in place of n in this case. Right? What does that mean? It means that your fraction, oh, this is becoming a dud, your fraction is 44 over 100. That is to say 44 out of 100. Right? You can simplify the fraction, but if it is already over 100, what is that automatically in terms of, in the context of percentage? Right? It's 44%, right, of the experiments. 44% of the experiments, all right, produced heads. Resulted in would be better to say. Heads. Right. This is again a fair coin flip, right? Some silly coin where it's heads on one side and then heads on the second side, right? Cheetah, pumpkin eater, all right? You could lower the terms of this fraction if you want, and that's respectable. But if it already happens to be over 100, do yourself the favor and just translate it to a percentage, right? Borrow these symbols and write them in that orientation. Here's one that is essentially the same idea. It's still empirical. Example 2, right? But you'll have larger figures to work with. So example 2, my paraphrasing of example 2, you could again print this out in a freeze frame here and read this. All right, and these are basically 3 examples here. In a drug trial, and that is an experiment involving a drug, not a political, not a legal thing, right? Drug trial that is supposed to lower blood pressure. Lower blood pressure. You have these situations. Of those that actually reduced participants, it reduced 379 times. It remained, the blood pressure remained unchanged. 62 times. And then it made things worse, it increased. Um, 59 times, right? In a drug trial, I should add, of 500 people, participants, right? These were the results. It reduced it for 370 blood pressure for 379 people, and it was unchanged for 62 people, and it increased. It made things worse. All right. For 59. I really shouldn't be laughing because that's terrible. But it increased. Bad drug. All right. Doesn't do what it's supposed to. All right. Let us calculate the probabilities based upon these empirical results. All right. We're going to use empirical, experimental, probability, whatever you want to call it, because these are a trial, which is a scientific experiment. All right. So in this instance, the probability of reducing blood pressure, all right, versus the probability of unchanging blood pressure. And then the probability of increasing. All right. In this case, again, we would have this incarnation of the formula, the actual frequency over the number of trials. Right. The actual frequency over the number of trials in this situation. Right. The actual frequency over the number of trials in this situation. Right. It's a little less descriptive when you have an F here as opposed to borrowing the event and rewriting it. But it's not complicated, right? Right? So in our drug trial of 500 people, participants, a drug that was supposed to lower blood pressure, these were the results. All right. The frequency for reduced would be 379 out of, what's the total number of trials in every single case? 500 people, right? 379 out of 500. All right, a big fraction. You could use a calculator if you want to reduce that potentially. Let's complete this thought. Unchanged, 62 out of 500. Right, and make things worse, they increase their blood pressure, 59 out of 500. These are the same experiment, it's just these are the results, right? All right, now, what does that mean? If you want, again, you can take your calculator and you could attempt to simplify these fractions, right, by using rules of divisibility. But rather than reinvent the wheel right now, you could just use this, assuming that you're comfortable with that. All right, there's a button here, A, B, C, all right? If in fact any of these fractions, and that one for sure, all right, because it's an even over an even, is reducible, you could enter 62, press ABC, and then 500, and it will automatically change it to the lowest form. So let me try the first one, 379. And then hit ABC, and you see this little L shape, backwards L. Over 500 shows up above. All right, that's the calculator's way of implying this is a fraction. All right, it did not reduce, so that's already in simplest form. All right, now if you wanted to convert this to a percentage, which might be more meaningful, all right, what you could do is try to translate it into a fraction over 100, or just simply divide the top thing by the bottom thing, right? What you're going to get when you do that when you divide the top by the bottom, what you end up with as a decimal is something that looks like this. 0.758, whatever follows it. Right, so times 100 would make it look like a percent, which has the effect of scooting the decimal over twice, right? So this is approximately 76%. Okay, not bad, all right, as far as the effectiveness of a drug supposed to lower blood pressure. Whatever side effects, right? Essentially the same idea here. 62 divided by 500, you would get something like 0.124, something trailing after it, all right, which times 100 has the effect of just scooting the decimal over. So this is approximately 12%. Right? I use percentages myself because I think it is a little bit more intuitive. Right? You're not really required to. I don't think you'll see it too much when you do your actual homework. All right. Okay. 59 divided by 500 is what is it? 0.118, whatever it is, trailing it, times 100, the effect of moving decimal twice. This is again approximately 12% because I'm rounding to a whole percent. All right. So 12, 12, and 76. Right. I'm not sure what the standard is to approve a drug, but that doesn't seem too bad. All right. If 76% of people actually reduce their blood pressure. I wonder who chooses these problems, I often wonder. It was me, I didn't come up with this. All right, now, we've gone through the two different types of probability, the experimental and the theoretical. Let me show you a slide to explain another concept. Get rid of that. Come on. All right, this particular slide is what I'm after. Let me back that off a little bit. There you go. This slide will be available to you in Canvas. I have to upload it still because I modified it yesterday evening. Is meant to illustrate the immediate difference but the long-term similarity of a coin flip probability, right? A theoretical probability essentially versus the experimental probability, right? Right. Here's some results from a coin flip, right? Right. This column of results is basically the theoretical, and this column of results is the experimental. So this is what should happen in theory, right? And this is what actually happens. Not, it depends on if you perform the experiment yourself. All right. Now, 10 tosses, all right? 10 tosses and the expected outcome would be 5 out of 10. That means that this would be a fraction of 5 over 10, right? If we're talking about a coin flip, again, there's only two choices, right? It's a half, times a half, a half every single time, right? 1 out of 2 possibilities, right? So if you did it 10 times, right? Right, it's still the relationship. 5 out of 10 is still the theoretical probability of 1/2, right? If you did it 50 times, right, in theory, it's 50 out of 100. That's still the probability of a half, right? If you did it 1,000 times, theoretically, it would be 500 out of 1,000, which is still the probability of a half, and you get the point, right? The theory is if you have a coin flip, and there's only two choices, really, of what it could be, heads or tails, then in terms of theoretical probability, it would be this, right? the number of outcomes favorable to heads would be just 1, all right? The number of possible outcomes in the sample space set is 2. So whether you did 10, 100, 1,000, 10,000, 100,000, these would be the results. That's what you would expect, all right, according to the theory. And then there's the actual situation, what actually happens, all right? Whoever did this, if they actually did, these are the results that they got. Let me use red, and hopefully this will help. 4 heads observed out of 10, all right? What's 4 out of 10, all right? It's not a half, all right? You could reduce it if you wanted to either the decimal equivalent would be 0.4 logically, or divide by 2 at the top and the bottom, and you get 2 out of 5. That's not a half, all right? In this situation, going along, continuing at the point of having done 100 flips, this is flips, so this is whatever you like, all right? There were only 45 heads, which would be 45 out of 100, right? You could reduce this fraction again, divide each of those by 5, I would say, right? Which would be 9 out of 20, right? 9 out of 20 is not a half, right? So you might go, everything is a lie, right? I wouldn't blame you. You'd be very suspicious, right? Rightfully so. Going along still, after 1,000 experiments, games flipping coins, right? Flipping 1,000 times. Imagine you had nothing else to do, all right? You'd have, and in this case, whoever tabulated this, only 546 of those flips out of 1,000 resulted in heads, all right? You could attempt to reduce this, all right? Now's a good time to use my calculator again. All right, 546 ABC 1,000, and you would get this, which is not too satisfying because of the lack of familiarity. It's 273 reduces to 273 out of 500. It should be. All right. Anyhow, that's simplest form for this ratio. 273 out of 500 is obviously not 1/2. Exactly 1/2 would be 250, right? All right. So it's exceeding a half, if you look at the numbers here, right? What's the point of this? The point is that over the long run, not individually, right, the theoretical and empirical probability will match, right? The key phrase there is over the long run, not immediately, right? That is basically saying the more experiments that you run, that is the more games that you play, you will see that this empirical or experimental probability approaches this theoretical probability over the long run, right? What is the point of this conversation? This is what is known as, sorry for the gobbledygook, right? The law of large numbers. The law of large numbers states that the probability apply in practice to large numbers of trials, right? Underline this, right? Not to a single trial, right? It is the relative frequency over the long run that is accurately predictable, not individual events or precise totals, right? What does that again essentially mean? I wrote my own little annotation here. Over the long run, the empirical probability approaches the theoretical probability, right? And you could see it reflected in this table here. Let me erase some of the gobbledygook, just not to get distracted. All right. If you analyze the decimal equivalence here, look what happens. There is one instance where it exceeded, but in just a limited 10 trials, basically, the decimal was 0.4 instead of 0.5. All right. And then after 100 trials, it inched a little bit closer. 0.45. All right. After 1,000 trials, it ended up exceeding 0.5, which is, I'm using as a decimal because that's a half, right? A half is 0.5. But more and more, 10,000 trials, look, all right, getting closer, 0.48, right, 5, whatever you want to say. And then 100,000 trials, imagine you did this 100,000 times, you'd come a break, all right? Eventually, what do you get to? You inch closer and closer to what is expected, 1 out of 2 or 0.5, right? But that is, again, over the long run, all right? So the reason I'm mentioning it is this. Theoretical probability is not a lie, all right? It's just that you would need to do this a lot in order to see that that is basically the long-term approachment, if that's a word, all right? It gets closer and closer to theoretical probability. Experimental probability approaches theoretical probability. Right? Otherwise known as the law of large numbers, meaning you need a lot of trials to see it. All right. Now, moving on. What time is it? Getting late. Well, all right, let's do example 5. And I will pull the curtain back in and turn my little light on. And let me just sort of paraphrase again. Do example 5, right? Example 5 in the packet, right? In a fair, not rigged, 52 card deck drawer as in pull, all right, determine the following. All right, and again, this is the kind of deck that I described before, right, where the set is basically 1 through 13 cards of a certain suit. 1 through 13, they labeled ace through king, of course, but of hearts, right, of spades, of diamonds, of clubs. Right. There are 6 individual problems here, so I'm going to try to confine myself again to 3 spaces here on the board, and perhaps ditch this marker once and for all. We'll see. The first one, A, B, C, is this situation. The probability of drawing an 8, right? Then the probability of not an 8, right? And then the probability of a club. Okay, we're going to be using, in this case, theoretical probability, so I'm going to stick with those formulas. All right. The probability of drawing an 8 would be the number of events favorable to 8 out of the total number of outcomes, the number of outcomes favorable to drawing an 8 over the total possible outcomes. All right. This situation would be things that are favorable to not 8, but still out of the same total. This would be the number of outcomes favorable to clubs. Again, the same total. All right. So, let's think about this. In a deck, right, how many cards, never mind their color, right, how many cards are labeled 8, right? There is, without having to dig for it, because it might take a while, because these are all out of whack. Oh, wow, that's dumb luck. Thank you. Thank you, universe, for helping me. There are... So sweet. Thank you. I really genuinely mean it, universe. All right. I didn't do this. That was a shuffle deck. Look what happened. Magic! It's magic! All right. There are 4 cards that are labeled 8. Never mind what color they are or what the suit is. All right. So maybe this is from I don't know. So that would be the number of favorable outcomes of this event. Drawing an 8 would be 4. How many cards are there in a standard 52 poker deck? All right, it's 52. All right, a fair 52 card deck. All right. Now again, you should try, if you can help it, to lower the terms. There's the simplicity of saying 1 out of 13 is a little bit more easily understood, right, than 4 out of 52. They're the same decimal, they're the same percentage, and if you wanted to, you could convert this to a percent. How so? Divide 4 by 52 or 1 by 13, and you would get something like, 0.7, whatever it is, right? So approximately rounded up would be about 8%, right? So if you're gambling, and I'm not trying to set a bad example here, but that would not be something you want to bet on, 8%. All right, now let's discuss this situation. What is the probability of not drawing an 8? Well, we've already isolated the situation, isolated the case where we have said, well, there's 4 out of the 52, all right? So those are the things that are 8, right? What are the things that are not 8, right? This would be, right, 52 minus those particular 4, right? Which makes what? That would make this as 48 out of 52. It's still the same total of 52, right? And again, if you reduce the fraction, divide by 4 here, divide by 4 here, you would end up with 12 out of 13, which is really close to being the maximum of 13 out of 13, right? So this is something like 92%, all right? Again, I'm not trying to encourage bad behavior, but if you were going to gamble, that's almost a guarantee. You'd win, all right, if this was the bet, all right? Next one. What about clubs? All right, I'm going to stuff these back in here now. There are how many cards that are labeled club, all right, in the set? All right, again, it would take a while. I don't know if the universe will be this generous this time. There are quite a few cards that are labeled with a club, all right? Jack of clubs, for example, is the king of clubs. And then, of course, those are the face cards, but the number cards, 7 of clubs, and so forth, all right? There are 13, all right? Total cards that are labeled as a club, all right? Again, how many total cards are there in the deck? 52, all right? You can actually reduce this fraction, all right? 13 times 4 actually is 52, right? Because 13 cards for 4 suits. All right, so this would end up reducing to 1/4, right? Which is exactly 25%. Again, not really something that you would want to gamble on because it's under 50, right? It's not really a good chance of it happening, right? What about the next slew of problems? Same example 5. Here. Example D, E, and F instead. The probability, in this instance, of a jack, I'm going to abbreviate as J, or a queen, or a king. All right. In this instance, the probability of a heart or a spade. Eventually, I don't want to bog you down with this to worry about, but the words and or are going to become important. Right now, you don't have to worry about it because they imply something. That is a discussion for another day. F is the probability, as concisely writ as possible, of a card, shall we say, that is less than 9 but greater than 5. Right? I'm abbreviating it by sticking the card in question between these two conditions. Right? It is less than 9, notice the point, and it is greater than 5. Notice the point is facing 5 instead. Okay? This is still theoretical probability. All right? So let us consider how many cards, right, essentially are this or this or this out of the total. How many jacks are there? There's 4 distinct jacks, right? How many queens are there? Similarly, there's 4 queens. How many kings are there? There's 4 kings. So how many is this total? 4 plus 4 plus 4, right? Since we'd be content with any one of these, right? That would be 12, right? Out of the same 52 deck. All right, which if you reduced it, I want to say divide by 4 here, all right? This would be 52 divided by 4 over 13, all right? Check my math, but I want to say that that is something like 23%, which is not bad, all right, but it's not great either. All right? Let's double check here. 12 divided by 52, yeah, it's about 23%. Okay. Probability of a heart or a spade, being happy with either of those. The number of things that are hearts and the number of things that are spades. And I'm using the word "and" somewhat liberally. Right? I should perhaps really more restrict myself to saying "or," I believe, in this case. Either condition is fine. How many things are hearts? Right? There are 13 cards that are hearts, right? And how many cards are not spaces? Spades. Maybe if I wrote it in the appropriate color, right? I'd spell correctly, but no. Right? There are 13 cards that are spades, right? Ooh, you know what? I just had a thought occurred to me. Let me just make sure that I'm not mistranslating the actual question. This is a good thing. 5. Okay. Oh, okay. In the case of question E, I have to specifically use this word. All right. It's the probability of something, of a card being a heart and a spade, right? That means simultaneously. All right, now the question is, right, can a card, and you could pick up a deck of cards and you could dig through it all you want, all right, can a card ever be those two conditions at the same time? Right? This is a heart, right? Never mind the number. It's a heart. Is it a spade? Right? No, right? This is a 7 of spades. Never mind the 7 for a moment. It's spades, right? Can it be a heart, right, at the same time? No, right? These two conditions that are being described here are mutually exclusive, right? There's a phrase. This is really a conversation for another day, but this term is going to be revisited. Mutually exclusive. Right? Meaning can't occur simultaneously. So the context of the the word "and" here is that something is simultaneously a heart and a spade. Now, the real question is, are there any cards in the deck of 52? This number is still 52 down here. Are there any cards that are these two things at the same time? No. So that means that it's 0 out of 52, which in terms of a percentage is what? 0%, right? It is a mathematical impossibility. It's a real life impossibility as well. Okay. All right. Now this is condition F here, is a card greater than 5 and less than 9. That is actually possible. All right. So think of the cards that are in between them. Right? Think of the numbers that are in between 5 and 9. Right? This is between these two, and they're whole numbers, right? I was reaching for black, and I got green, and it worked good. 6 is between these two, 7 is between these two, and 8 is between these two. All right. But in total, how many cards are essentially 6, 7, or 8? Out of the sample space. Well, there's 3 6s. Pardon me, that's stupid. There's 4 6s, all right? And there's 4 7s, and there are 4 8s, because there's a 6 of hearts, a 6 of diamonds, a 6 of clubs, a 6 of spades, and the same situations for 7 and for 8. So if you added these, what would you get once again? 12. And the number of cards in general is still 52. Right? So what would you get with as the same fraction? You would reduce this to 3 over 13, which is again rounded as a decimal percent, would be approximately 23. 23%. So again, not so great. The only situation described here that would be, pretty good gambling would be B, right? Not 8. Now, I finally get to show you my diagram that I made, and I'm so happy because I'm proud of it. All right, so let me do that now. I hope that this, what you're about to see, summarizes a lot. I made it for that purpose. If it needs a refinement, then eventually that will happen, but here is my diagram, which I have prepared for you. All right. To zoom in, I will. All right. Here are some facts about probability. Facts. I'll zoom in just a wee bit. No, that's not a wee bit. All right. Here are some facts about probability. Again, I abbreviated probability, P-R-O-B. Probability is mostly written in the style of a fraction. Why am I bothering to mention that? Because when we do section 11.2, when we talk about odds, that is also a possibility. You can write something in the style of a fraction, but it isn't mostly written that way, right? So probability is mostly written as a fraction, all right? Which means, all right, probability can be converted to a percentage, right? There's nothing wrong with doing that, right? When we get to odds, this is a no-no. You don't want to do that, all right? Now, how does one convert anything to a percentage? I want to remind you of my little diagram that I gave you a while ago. Right? You can convert any one of these 3 things, given them, right? And here's how you would do it. If you have a fraction, right, and you want to convert to a percentage, meaning dot, you start here and you go here, you multiply by 100, and you use that symbol, right? If you start with a decimal, dot, and you go here, it's the same process. Going to a percentage, you're multiplying. Coming from a percentage in either event is dividing. The effect in a decimal is moving the decimal points 2 spaces to the right. All right. The effect of dividing by 100 is to move your decimal place 2 spaces to the left. All right. If you were converting from a decimal to a fraction, right, the place value of the far right digit, the far right place, that's your denominator. All right, so whatever digits that you see up to that point, that will be your numerator, and you can reduce it as in the style of fraction. More likely what you'll do, because you have a calculator, is you'll start with a fraction and you'll convert it to a decimal. There's a button on your calculator that will actually do that for you, but the technique involved is divide the numerator by the denominator. That is to divide the top by the bottom, essentially. Right. And then you could, in other words, rather than go from fraction to percent directly, you could sort of do it indirectly, meaning you start here, convert to this, and then convert to that. That's often what happens. It doesn't have to happen that way, but it often does. All right, that's just a review. All right. On your calculator, again, if you're curious, there is a button here, and I'll show it to you. Up here towards the top. It might be a little bit hard to see in the dark, but I want to say this button here that you see in the lighter blue, FD, if you had something written in the style of a fraction, let's test the theory, 1/2, you have something written in the style of a fraction, if you engage that second function, it should convert it to a decimal equivalent. You know that a half is 0.5, so equals, there you go, yep, it works. Anyhow, that's old hat, right? You know that already, right? But bear this in mind. Mostly written as a fraction probabilities, but they can be converted to percentages, and this would be the technique involved. All right? Odds, which you will see forthcoming, not today, but on Thursday, you can't use percentages. All right? Now, these are rules that are adapted from, or facts, borrowed from your book in the order that they show up. This is just sort of my paraphrasing, all right? Basically, the information that you see on, what pages of? Here, this page, I'm summarizing these two things, all right? A maximum probability, that is the probability of some event, whatever it is, pardon me, the minimum probability is 0, all right? Which as a percentage means what? It means 0%. And in effect, what does that mean really? It means that the situation is impossible, right? It is never going to happen, whatever is described here, right? What's the maximum probability that one could get? Right? Well, the probability of whatever event is a maximum of 1. Remember, if we're writing fractions, in theory, it could be 1/1, or 6/6, or 100/100. Something like that translates to 1. All right, what is that in the style of a percentage? 100%. What does that mean in effect? It means that it is 100% certain, no debating, it's going to happen. All right? Definitely going to happen, never going to happen. So if you have 0, impossible, 1, it is a certitude. All right. Now, what is probability in general? It is a non-negative, all right, which means that it can either be 0 or generally some positive fraction, all right. If I wrote it in this way, all right, I'm using math symbols, it would basically be this. Your probability is essentially between this maximum and that minimum. So the orientation of these inequality symbols would be like so, all right. It's greater than 0 or exactly equal to it, or it is less than, because the point is facing this, less than 1 or exactly equal to it. Right? It's some fraction that would be in between this spectrum here, the boundaries here and here. All right? Moving down, these are very useful, these formulas that you see here. The sum, based upon this and the prior information, the sum, that is adding, of all probabilities of a game, experiment, whatever you want to call it, should be nothing more than 1. Right? It should be exactly 1 if we're talking about, indeed, all possible probabilities. All right? What does that mean? It means that if you had some specific event, I don't know why I put my leg there, the probability of some event A, right, plus the probability of things that are not A, which remember from set notation, you might want to zoom in on this, a little bit off, okay. The probability of some situation that is not A, also known as the complement of A, that is everything that isn't A, would in theory be 1. Right? When we're answering questions that are asking for that complement, right, we could take advantage of that relationship, essentially. Right? Remember, there's an alternative way of saying not 1, which is A sort of an apostrophe or a tick mark, all right, aka A prime. A prime, if you want to get fancy, right? That is, again, set builder or set notation speak, right? Instead of spelling it out somewhat verbally, not A, right? It means the same thing, all right? If you subtract from the whole, you will get the other chunk of the whole, right? Right? This is a chunk, that is the whole thing. This is the other balance of the chunk, the balance of the whole. Okay. All right. Now, as a fun example, I thought to illustrate this, I threw in an extra word problem, which I'm going to show you now, and that's this one. All right, this is from an older book. All right. Suppose that you have a 2-pound bag of Hershey's miniatures, and they contain the following: 33 milk chocolates, 27 crackles, which is like a crunch bar. 26 Mr. Good bars. I tried to color code these, which is milk chocolate with peanuts in it, if you're not familiar. And the one that I actually like, which is the special dog. Right. Anyhow, we can answer these. Just given that much information, all right, we could find the theoretical probability of the following. All right. I'm going to have that much here. We're going to find the theoretical probability of randomly selecting a Mr. Goodbar. All right, the theoretical probability of randomly selecting a crackle or a special dog. All right, and then the theoretical probability of not selecting a milk chocolate, which implies a lot. All right, what we would do as a preliminary step is taking all of this into consideration. All right. How many things total are there? Right? This is to figure out how many elements in the set, basically. What's the sample space? Right? If you added 33, 27, 26, and 19, you should get, I believe, 105. Right? 105 elements in the set, in theory. Right? Now, to answer A, let me try to confine myself to just this much space. And I'll put B here, and then I'll try to do C here. That's becoming a dud. All right. Mr. Goodbar, right? How the probability, I'm going to write this in sort of probability speak. Mr. Goodbar. Right. Mr. Good. All right. The probability of randomly selecting a Mr. Goodbar, right, would be the number of outcomes favorable to drawing a Mr. Goodbar out of the total in the set or the sample space. Right. So how many Mr. Goodbars are there? Right. It would be 26. And how many are there total in the bag? All right, 105. So you have this fraction, as you can see, of 26 out of 105. Right. If you reduce the fraction, right, you could whittle it down by rules of divisibility. Well, I'm going to cheat right now for the sake of time. And it's not going to get into anything meaningful, so no. Clear. Dark. 26 over 105. It's not going to reduce, that's in simplest form already. All right. So let's make this into a percentage because that is universally understood. All right, 26 divided by 105 is 0.247. 0.247, some trails here. So this is about 25%. To give you a feel, right? Sorry, this is dying too. Let's see, moving on. crackle, all right, or special dog. All right, if I were to take this and sort of try to write it concisely in probability speak, all right, it would be the probability of a crackle or special dog. I'm going to put it just as crack or dog, all right? In which case we're going to be considering the number of outcomes that are favorable to crackle or dog over the total number of outcomes in the set. Right? That's how you would translate, right? How many crackles are there? 27. So let me put this in blue maybe. 27 crackles. That should have been red, right? Because that's what the wrapper looks like. It's something like if you've never had it, it's like a crunch ball. I think a crunch ball is better personally, but that's just me. Special dark, which is quite tasty. All right. This is dark chocolate, and dark chocolate is the best chocolate. All right. 27 and 19. If you added those, what would you get? Let's see. It looks like 46, right? So overall, this would be 46, and this is still out of 105. So perhaps you could reduce that, but let's get the decimal instead. Right? If you divide 46 by 105, you should get something like this. 0.438, which is about equal to 44% chance. All right. 44% of the bag are these condition. All right. 25% is that. All right. Let's see. Not a milk chocolate. Now here's where we could use the complement formula, right? There's really a couple of different ways you can do this. You could just intuitively go, well, I'll just exclude, milk chocolates in my calculation. I'll just consider what these are. But you have the option if you use the complement formula, which is basically the condition here. I'll write it as the probability of not milk chocolate, right, would be equal to 1, this is the complement formula, minus the probability of the things that are milk. The advantage to this is that you could work with maybe smaller numbers, right? Because you're just considering. I don't know if that's necessarily true. I like this formula. I'm not trying to corrupt your opinion, but if you don't know a lot, right, other than milk, you could do it either way. To be fair, all right. Let us see. What is the probability of this by itself? That's the number of events that are favorable to milk out of those in the sample space set. All right. Number of milk chocolates, 33. So that means that this is essentially 33 out of 105, right? Without doing anything else, all right? It's 1 minus 33 out of 105, right? If you're familiar with fractions, of course, you could translate this to something that has a common denominator, all right, which would make 105 out of 105, that's 1, right? And then subtract just 33 out of it. Right? I think that's more efficient, quite frankly. Anyhow, what would you get? Right? You should get 72. Right? So to answer this question, you would get 72 out of 105. Right? And that as a decimal would be something like 0.685, which is approximately 69% likely. Right? That makes perfect sense, right? Because this is the majority of stuff that you have to choose, right? 27 is as close to 33 as you could possibly get in this situation, right? Then have another 26 added to that, and then another 19 added to that, right? Whatever this sum is, all right, is an alternative way of calculating 72. It would be 72, I guess, right? All right, 13, yep, that's it. This is 72, right? You could add to get to the answer, or you could subtract from a whole. All right, that's really the point to illustrate here. All right, so 69%. moving on. All right. Let me just show you the discussion of genetics that came up here. Because that has to do with probability as well. All right. There's this page from your textbook that is interesting. All right. It's about Gregor Mendel. All right. Gregor Mendel was, I forget what order monk, but a Catholic monk of some sort from the 19th century, so the 1800s. And he had an interest in, he's considered the founder of genetics as a study. All right. Anyhow, what I would highlight is basically this. Gregor Mendel developed the laws of heredity genetics by crossbreeding different types of pure pea plants and observing the relative frequencies, all right, of the resulting offspring. These laws became the foundation of the study of genetics. For example, when crossbreeding, this is the real revolution in thought here, when crossbreeding a pure yellow pea plant, right, and a pure green plant, all right, the resulting offspring from the first generation at least were always yellow, all right. So even though they're parents of one of each, right, a yellow parent, if you will, and a green parent, right, the offspring was still going to be yellow, right. Now the result, the conclusion here is that genetic trait, among other genetic traits like the smoothness or the wrinkledness of a pea, right, the trait that is shown up in the offspring is what would be regarded as a dominant trait, right? And a trait that might eventually show up over several generations, all right, is a recessive trait. May eventually show up. After several generations. All right. This is what shows up in first generation. Know those words, dominant and recessive. This is the kind of thing that you would discuss normally in genetics, in a biology class. All right? And here is another diagram to illustrate. All right? This is a little misleading, what you see here. All right, so let me just read you this. Mendel then crossbred the offspring of the first generation, resulting second generation offspring had both the dominant and recessive traits of their grandparents. That's what I mean by may eventually show up after two generations. All right. What's more, these traits always appeared in approximately a 3-to-1 ratio. This is more like odds, the way that this is presented, like odds than probability. They're really discussing the same thing, but it's the shall we say, odds speak versus probabilities speak. You know, manner of talking is what I'm getting at. All right, 3-to-1 means that there's 4 things involved here. All right, but it's presenting it in favorable to one situation or another. All right, that's again a conversation for section 11.2. Anyhow. What that means here is that this P here would be divided into 4 segments, 3 that are yellow and 1 that is green, all right? And in this situation, the way that they're illustrating is that this would be 4 segments, 3 that are smooth and 1 that is wrinkled, all right? Now, how does this relate to us at all? Well, I drew a little diagram to help illustrate what's going on here. In genetics, what normally happens biology class, I should say at least, is the discussion of something called Punnett squares, which is a way of predicting, right? It isn't a guarantee, but it's a way of predicting. It's a discussion basically of probability. Right? So, I put this little thought here. What's good for biology is also good for mathematics, and you'll see why. Right? Let's take a discussion of brown eyes, and blue eyes. Right. Brown is the dominant trait. Most people on Earth have brown eyes, right? Blue eyes is a recessive trait. That's why I'm using lower cases on purpose, right? Dominant is, capital letter, right? Capital. All right. So, if you can imagine that your parents, all right, or imagine two parents in general. Let me use red and blue to kind of make two parents. Right? And their genetics in terms of eye color constitute this much information. All right. Suppose that your mother here is a person that is brown-eyed because brown is dominant, right? But they're carrying a recessive gene, right? Brown-eyed, but carrying recessive gene. Recessive blue. Meaning that they themselves are not blue-eyed, and it might in fact be more complicated than this, but it still works, right? They're still carrying this trait. And they get involved with a person, Papa here, right, that has the similar situation going on here, right? That is also brown-eyed, right, but also a carrier of this recessive trait. What should the offspring, in theory, look like superficially? All right. Well, let's cross them and we'll find out mathematically what this is predicting here. This is Papa, right? All right, and this is Mama here, right? According to Punnett squares. Well, they have, let's see, one cross would be BB, all right? Another one would be similar to both of them in this context, right? And then a second one here. And then there's this other possibility, BB, right? Now, a couple of things to point out here. This is very simple. It's not taking into consideration other things like a person who is gray-eyed or green or hazel, all right, or even people who are born without the color. Some people have reddish eyes. It's rare, but they lack pigmentation somehow. Right? What this is predicting, and it's the reason why it's interesting, it's predicting that 1 out of 4 possibilities is a blue-eyed offspring. Right? That's not a guarantee. Mama and Papa here going to have 4 kids, right? And as you know, law of large numbers. I mean, this may not actually work out that way. It's just it's a prediction, right? If in theory they had 100 kids, all right, 25% of them, because if it's 1 out of 4 is a 25% chance, right? Then that will demonstrate that mathematical possibility, all right? The more and more children that they have, that will be more and more closer to the theory prediction, all right? But this is really what it's just, I'm stumbling on my words a bit, but the purpose of Punnett squares is to make a to predict, right, what is possible, right? If you have a hybrid, this would be referred to as a hybrid mother and a hybrid father, that is, they carry both the dominant and recessive trait. They are brown-eyed each themselves, right? But they're carrying the recessive trait. It's more likely, right? It's more likely because dominant B, dominant B, dominant B in all these cases. 3 out of 4 brown, right? Because it's a 75% chance there, right? Greater than 50 is, probably what you're going to see, right? It's probable, right? But there is the faint possibility that their kid would be blue-eyed, right? If they themselves are carrying that recessive trait, right? Both of them, right? All right. Now, what does this have to do with math? Well, a long time ago, I worked in a school where one of my coworkers shared with me something that she herself was taught. And I always thought this was very clever, right? You could apply that concept of crossing, as you would for genetics, Punnett squares, to distributed property, is essentially what will be happening in an algebraic expression times an algebraic expression. So suppose, for example, that you had this problem. All right, x plus 2, all right, times x plus 3. All right, if you think of the first factor here as basically being mama again, and the second factor here being papa again, all right, then you could kind of work it in a similar way. Right. Now it's applied to just purely numbers and not something biological, but it would in fact work. Watch what happens. All right, cross these two. It's xx, but what's the abbreviation for that in math world? X squared, right? What's the crossing of these two? Plus 2x. And what's the crossing of these two? Plus 3x. And what's 3 times 2? 6. And what you end up with is the solution to the FOIL problem, right? What normally is regarded as the instruction of FOIL, first outside, inside, last, all right, written inside Punnett squares, which means that you could get to the answer this way. It's kind of clever. The result would be x squared plus the sum of these two is 5x plus 6. I always thought that was great. So I felt like propagating that. I wish I can give credit to the originator of this idea, because it's very insightful, but you could see that there is a parallel here, is what I'm getting at. Okay? Anyhow, we're at 2 hours and a quarter here, so let me stop, and I'll upload this video and the materials. Okay? Let me turn that off. Come on. And just remind you, all right, for homework, do section 11.1 in my lab. And if you do, you're all there and you're all squared away. All right, you're right where you're supposed to be. Sorry, that's very faint. Okay, all right, thank you for sticking with me, and I'll see you again on Thursday. Be careful out there.